It's an hour longer. No. It's not longer to get there. It's for some people, but you would have got there.
I talked to him, but I don't want to say
It's an additional.
Yeah, I saw him from that.
I was so upset. I'm super upset.
Yeah. I gave the Boy Scout cheers for Christmas, and I got them on sale. I might have told you guys already, I apologize. And I got them on sale at Staples Church, Black Friday, and I got them over half price off. And they delivered me the Staples down in they didn't charge me sales tax.
Are you gonna come here with me?
So, and I got my, member discount, so it worked out good.
Yeah.
Art was teaching me all about.
Art has to teach me all about RTDs and things several times a week, but I still don't have it.
It's all that they can lift up. Yeah, that's what CC and I went over what the details were. So that's a step.
Don't make me upset, I have to explain it and I can't, I never get it right.
The other one that says to me, he says, yeah, it's sort of like one. Yeah, I like one. But he says, you know what, one else just keep running all the time. I spend my money on it, and I can voice my own money. This is the one that does this thing over.
Just clap 3 times and lose 50.
Yeah, he's got a great one.
That would be good to start sneezing.
And take care of the ones at yeah, exactly.
You should calculate that backwards from like 45.
People would start lying.
That'll work great.
oh, no, big road. Oh, yeah, plus no air conditioning. Yeah, I was too little to
You ready? All right. Hello, everybody. Thank you so much for joining us for Superstellar Friday tonight. Tonight we have Shyang Puri from RDF Corporation based in Hudson, New Hampshire. So RDF Corporation is one of our newest corporate members here at the Discovery Center. So that's really exciting because they make programs like this possible behind the scenes and then tonight in front of the scenes. So Shyang's going to talk a little bit about the history of the corporation. She brought some engineer friends to do a demo. So let's put our hands together for Shyang. Yay!
All right. Hi, I'm Shyang. Thank you all so much for coming to our talk. Thank you also to Amanda Leith for the invitation to come speak a little bit about RDF's 70 plus years of history contributing to space exploration. And actually, Amanda is a little bit of an RDF legacy. Her dad, Kevin, was an engineer at RDF for years. Many of us see his name on drawings every day. So oh, he's in the audience. There he is. Well, actually, great. Kevin is sitting right next to Art Pearson, who I have to call out. So Art, despite having been retired for years, is the person who I ask questions to about what we do several times a week. So please direct all of your questions later towards him. He has all the answers. I definitely have limited answers and will probably just call or text Art to get the answer. So Art Pearson was the sales manager at RDF for countless years, pilot, veteran, and all-around expert on all things. So very grateful to have him here, and also welcome to all the RDF team who are here tonight. Oh, you can't hear me?
I can't hear.
Oh dear.
Do you have a microphone or something?
I don't, but I will shout if you need me to. I don't think that's for projection, right?
Yes, that is for the Zoom account online.
All right, I'll be loud, and if you can't hear me, just say something, and I'll shout louder. How about that? Okay. So a little bit about RDF. So we are a small business, about 60 people in Hudson, New Hampshire. We make temperature sensors. So these are sensors used to understand what the temperature is. Very simple, very straightforward. We've been in Hudson, New Hampshire for years and years. And all we do is temperature measurement now. We don't do anything but temperature. And we have been a part of the space program since the very beginning of the space program. We have been on every manned US space flight, beginning with Alan Shepard's first Mercury Redstone mission. So our roots go back to the 30s. RDF is named after its founders, Arthur Ruge and Alfred de Forest. They were both MIT professors in the 30s, and Arthur Ruge is credited with co-inventing what's called the strain gauge. This is something it's a sensor that's in everything you have all the time. It helps you understand how much strain or stress is being applied to something. And at the time he invented it, along with another gentleman, Simmons at Caltech, nobody really thought there was any value in that. Nobody wanted to commercialize that at all. Both Caltech and MIT passed on the opportunity to patent the technology. They actually all agreed to let Ruge have the rights to the strain gauge. And so actually Arthur Ruge, very shortly after, went into business. He and DeForest formed a partnership to market the strain gauge, and they hired Frank Hines, who was Ruge's lab assistant. And the three of them together created a consultancy and started making and selling strain gauges. And not too long after that, also started making and selling temperature sensors, amongst a few other things. That quickly became adopted in the aircraft industry. My understanding is that our earliest customers were in the aircraft industry. Most notably, Hamilton Standard at the time was making propellers for planes. Still the 30s and 40s. Still planes, not space, right? So the strain gauge was adopted to measure stresses on the propeller, and then they were like, hey, guess what? We've figured out how to give you a temperature measurement on your propeller, on the surface of your propeller. And so in many ways, our earliest temperature measurement technology involved a flat surface style measurement, and this was novel. We didn't invent the temperature sensor. RTDs and thermocouples, which I'll explain what those are, they were invented in the 1800s. But making a surface measurement, being able to tell the temperature on the surface of something rather than inside of something, that was a big innovation. And so eventually, they realized they needed to split these businesses. And so the strain gauge technology went to a business that became known as BLH, or Baldwin Lima Hamilton. Some of you may be locomotive fans, and you may recognize Baldwin and Lima from that. And the temperature sensor technology went on to become what is today RDF. Actually, this is the original strain gauge that he was awarded the patent to. You can see them at the MIT Museum in Boston. So in 1955, it became clear that they needed to move someplace from Cambridge, Mass, where they could have more space to build and design these temperature sensors. And so in 1955, what was then known as Arthur Ruge and Associates moved to Hudson, New Hampshire, one of the first companies that was poached out of Boston by the state of New Hampshire. And the only one on our street, Elm Avenue, to have survived all of those years. Actually, RDF has slowly expanded into the different buildings abandoned by the other businesses that had been enticed into Hudson at the time. Hudson is, of course, right over the border from Massachusetts, so it was an easier sell at that time. And so they moved in, they made a big announcement, and they started to set up shop. You can see they very quickly became busy. It's my favorite picture. I also feel it's an accurate representation of my desk today. Just a total mess. So at this point, you may be wondering, again, what are temperature sensors? And so really, again, temperature sensors are small components used to evaluate what the temperature is someplace, but they don't provide you a reading. They don't do anything. They're completely passive. And what happens is actually, you can imagine an electricity is run through a sensor, and either using a resistance measurement or a voltage measurement, you can work backwards to understand what the temperature is. So I'm going to call up my colleagues Nate and Kevin to show off a little bit what these sensors are and how they're made. Come on up. We wanted to have a visual for you all, but it's not working, so they have to do a little display action themselves. But we're going to start with description of what an RTD or resistance temperature detector is. And so this is a sensor that provides a resistance output. So that means that you're measuring a resistance, which is a value given in ohms. Some of you may recall from your earlier physics lessons, ohms for resistance, and working backwards from a value in ohms, you can determine temperature to a fairly accurate degree. And so you can actually see here, the traditional typical format of an RTD is in this cylindrical coil format. And that is an RTD, which again, RDF did not invent, but which existed from the 1800s onwards. And typically we use platinum to create this element in the center, this being the element. And then platinum in a very high grade or a nice grade of purity, excellent grade of purity, can then yield an accurate temperature reading over a very wide range. But there are other materials that have always been used for RTDs as well. Some of them are nickel, also copper, and sometimes tungsten for very high temperature measurements, because platinum tops out at around 600 something Celsius. But in any case, this is a very, very small diameter platinum wire, and it was RDF's innovation to create some of these jigs and fixtures, which enabled the manufacture of these sensors in Hudson. You might be able to make out a very thin wire there. So here we have an example of an RTD temperature probe. So inside this probe is basically something very similar to what you see here on the screen. Just here it is in a stainless steel probe. And it's in a beaker of dry ice. And Kevin, what is the temperature?
Well, dry ice can get very, very cold. In fact, this dry ice here, we're measuring it around minus 90 degrees Fahrenheit. And keep in mind, we're still getting lower with the temperature. Because Shyang is just taking it out of the dry ice, there's a certain response time attached to that. You're not going to instantly go from the current temperature to a new temperature if you just start changing temperatures with that.
That's exactly right, Kevin. You're totally on the money, because dry ice, of course, should be around minus 110 degrees Fahrenheit, but that's not the reading that you have
Looking
yet.
about minus 98.
Slowly getting down there. So this actually highlights some of the challenges of temperature measurement, because the RTD is not broken, and the RTD is not slow. Actually, the RTD is trying to take measurement in a loose grouping of dry ice that's, you guys can't see, but it's in pellets here. There's giant air gaps. Here, I'll hold it up. There's giant air gaps in there between the pellets of dry ice, all of which minimize the RTD's ability to get a good temperature reading. It's not well immersed in the dry ice, and so it's harder for us to get that minus 110 degree Fahrenheit reading that we would have been expecting of the RTD in this setting. That, and also we are limited by the machine which is hooked up to it. This is a data acquisition system which is hooked up to the RTD. It's converting this resistance reading, doing some math, and then plopping out the temperature measurement or the temperature reading on the other end. And so all of these factors are coming into play, limiting what would otherwise be a very strong performance of the RTD. Because again, the RTD doesn't do anything, it's just sitting there. All of these other factors in its environment are contributing to what the readout is.
Another thing I'd like to add is some of the challenges that come with making temperature sensors is the application you're going to use it for. Some of our elements are just sandwiched between like polyurethane tape or some sort of material that heat can travel through very easily. But the problem with that is it's usually very weak. If you're going to use it in some kind of space environment or a military environment where it might have to go through tough conditions, you might need a sensor that's more robust and stronger. But as a result, the temperature, the heat that's getting to our sensors has to travel through stronger materials, usually metals, materials that may not be as conductive of heat as something that's thinner. So that's one of the challenges that we have to solve with our sensors when we are thinking about applications and other factors tied into that.
Kevin is totally right. So here we have a view of what a surface style RTD would look like. So this again is one of RDF's original innovations, is to design this surface style measurement. And you can see that instead of the cylindrical format, you now have a pattern where the element is wound back and forth in a flat style, right? And so actually we have one here. This is RDF's model 22810. You can buy them online. It's one of our most commercial products. And also very similar, honestly, to ones that have been flying since the 60s in space. And let's see, what's my response time on that?
We are climbing down, we're around 32, we're getting colder.
No, I'm not getting a good assurance, honestly.
We're still dropping, we're around 0 now, and we're very rapidly climbing towards actual temperature.
All right, I'm gonna pass this off to Nate because I'm done. You wanna immerse it? We'll see if it should get down there eventually.
So you can see as we took that sensor out, we rebounded back to about 32 degrees, a much higher temperature than when we had taken the metal RTD out of the dry ice. So when comparing these two sensors, if you were looking for an application with good time response or how fast you can recover to the actual temperature, you would probably choose our wire wound 22810 over the metal probe sensor, if that is what you're trying to optimize.
And if it works for your application. Yes. So again, one of the primary differences between a probe and a surface style measurement, again, is on one, you're measuring literally the surface of something, and with the probe, you're measuring the inside of something, or you're measuring a fluid maybe that's going past it, or a gas that's going past it, something like that. Yeah, so it'll get there. Again, a really not optimal way to get this these sensors into the medium that they're supposed to be measuring. A couple weeks ago when I found out we were gonna do this, I asked Nate here to come up with like any idea he could for how we could maybe get liquid nitrogen into this museum. And I feel like Nate really worked at that, but we eventually arrived at the conclusion that I would be wrong to do that and would likely freeze everybody and cause an accident. And then we even were playing around yesterday at the office with a solution of the dry ice in isopropyl alcohol, but then we found out that we might not be able to dispose of it here without causing a problem, so we had to drop that too. But that was fun for us. So yeah, basically an RTD is a sensor, gives you an output in ohms, a value in ohms. It's a resistance value, and it helps you determine the temperature. Another type of temperature sensor that RDF makes is something called a thermocouple. Any of you that work on your furnace at home or your car, you may have used the thermocouple here or there. Very mature technology, again, been around since the mid or early 1800s. But a thermocouple works a little bit differently. A thermocouple, instead of having a single element made out of a single material, a thermocouple works by having two dissimilar materials joined together, two dissimilar metals joined together. And when joined and when there is a electric current run through, there will be a voltage difference which converts into temperature measurement. Or rather, that voltage difference can be correlated to temperature and will depend on which materials you chose to join. And so for that reason, thermocouples always conform to a standard type. These are agreed internationally. Very common types are K, J, T, and E. We've got a few of them plotted on this graph. So you can see that over a temperature span of minus 250 C up to 1750 C, they each perform differently. They each give a different microvolt output depending on the temperature. So that's basically what a thermocouple is. And RDF been making specialty thermocouples for a very long time, but in the 60s, I believe Frank Hines, the third employee at RDF, he's credited with inventing a proprietary material, a proprietary thermocouple material. So again, the materials themselves not different to what the standards are, but the format of it was in a foil. That foil, we still make it. Actually, Ryan over there rolls it out every once in a while. That foil is about 12 microns thick, and it enables practically instant response time. So what that means is the moment the temperature changes, you know, and that can be very valuable depending on the application. And resulting from our capability to make that foil, which we still make, we also developed something called a heat flux sensor. And so a heat flux sensor is a little bit different from a temperature sensor because it actually provides not a temperature reading or temperature measurement, but a measurement of the flow rate of heat. And so you may remember back from school days, heat and temperature not exactly the same thing. Heat is I'm going to say this wrong, but it's basically like an energy versus just temperature. And so we are able to provide people a reading of the rate of flow, and also the direction of that flow through the heat flux sensor. And actually, in preparing for this presentation, we found a proposal that RDF made to the Apollo program in 1963, one of our earliest heat flux sensors. So yeah, we actually have a few of them here as well. We can maybe give you a demonstration. Well, we can start with the foil thermal. Where are they? All right, so here, Nate's got in his hand one of our foil thermocouples. This one's actually been laminated, so that just means that the thermocouple you see pictured here, which again is just 12 microns thick, extremely hard to pick up and put down and touch and move and whatever. And so we also make them encapsulated in a very thin, basically plastic sheet. It's polyimide sheet. And that enables you to pick it up, move it around, stick it down, so on, without damaging it. Yeah, why don't you show us how quickly that gets hot?
So right now we're at room temperature about 75 degrees. If we were to apply to the heat lamp, we're already at about 430 degrees. We're pretty much right at the temperature rating of our heat lamp 450. See, as we move into the dry ice, we are already shooting right around minus 60, minus 70, getting to our dry ice temperature relatively quickly.
It's still waving around in the air, but you can see the difference in the response time, and that again comes down to the thinness of the material, and basically it's a low thermal mass material. Yeah, that's both of them a couple. And you want to show that heat flux sensor off? This is actually my favorite product of ours. Every time I travel and explain about RDF and try to explain our products and what we do, I always start with the heat flux sensor. Here, go ahead and
So-
show it off.
Well, I was actually gonna say, Nate, if you were to sandwich the heat flux sensor between your hands right now, because both his hands are, I'd assume, the same temperature, or close to the same temperature, you will actually get a low reading out of our heat flux sensor. And that's because the rate of change is low. If both surfaces are the same temperature, then in a perfect world, you're actually getting 0 heat flux output. But if you were to take one end of the sensor, put it on, say, the heat lamp or the dry ice, and compare it to the outside, you would be getting a higher heat flux output because one side you're running at about 450 degrees, the other side is, if insulated, room temperature. So that's how the heat flux sensor is reflecting the rate of change of heat rather than the measurement of heat that you're at, the measurement of temperature.
Yeah, actually, we have a piece of old space shuttle insulation material that our engineering manager dug out of a closet for us. This is obviously it's heat shield material, so it's designed to be extremely insulating. So if Nate's holding the heat flux sensor, I don't know, you could hold it even further away. You could hold it like 6 inches away or so, and you should be able to see some changes in flow rate, if you could see this, which you probably can't. But then, of course, if you were to hold insulating material far less insulated than this, between the heat source, there should be a change you can see. But actually, one of my other favorite demonstrations of the capabilities of this sensor is actually, if I had my cell phone on me, I would shine a LED flashlight at it, and this sensor is so sensitive that would have an impact. So even light sources versus heat sources will have a major impact on the sensor, and you would be able to get a reading. All right. So you've now had Temperature Sensors 101, and you're all qualified to be temperature sensor design engineers, I'm sure. But I think there's probably still a few things you may be interested to know about temperature sensors, especially in the space environment. Thanks, guys. I think we're good for now. Oh, yeah.
So that last one you showed, it appeared it's not really designed for static temperature. What would be the ideal application that you would use that?
Yeah, well, so my favorite example is you can imagine in the cold vastness of space that it's basically absolute zero, right? And so a lot of systems that are up in space, like a satellite, for example, they don't work if you don't build in heaters. So, which are also something that we do build, but so you have to manually heat the system, right? But then you have a problem because you don't know if it's, rather you have to dissipate that heat as well. You can't just have it all be in there collecting. So you always have to have thermal management systems in a satellite, for example. And so a heat flux sensor would be an ideal way of monitoring if that thermal management is working.
Or if you'd be looking, if you're getting a result, it may mean something's wrong.
It may. So another great example there is you can imagine all of these systems up in space. They're very often, they're pretty expensive and specialty battery systems installed. And so batteries have a function where they can sort of overwhelm. They can have what's called thermal runaway. And so one way to monitor for thermal runaway is to monitor the temperature, which is obviously going to be increasing. But it turns out that if you monitor the heat flow against that battery instead, you'll have a much earlier indication that runaway is taking place, enabling you to shut down before that happens.
Hope to see a straight, flat line.
It's not though, it's a curve, right? So it's a curve. And so thus monitoring for the heat flow earlier enables you to shut down earlier. Yeah. I'm still shouting. Can you guys hear me? Can I talk less loud? No? Okay, I'll stay at this volume. Okay, so what I always try to explain to people about temperature sensors is that the sensor is just one part of what we do, actually, and the sensor isn't always where the innovation is. It's sometimes in the packaging of that sensor. So it's what we put around it and how we get it where it needs to be that is sometimes the big design challenge. And so a lot of what we do at RDF is figuring out the form function of these sensors rather than, what they do. So you can see here a variety of probes. Each of them has a different form function. Each of those is optimized for the application it was installed in. So something like this little guy, which has a connector on the back end, lets you plug it in, pull it out real easy. It has a standard sort of small 1/8 inch diameter probe tip over there. It's helping insert the RTD into a flow. And then you can't quite make it out probably, but there's threading around it here, which enables you to screw it in the pipe it needs to go through without there being a big old leak and so on. Pretty simple, pretty straightforward. But over here, you have a picture of a probe which was used in the space shuttle in the fuel lines. It has at the top there a hollow area, and the sensor is wound around that hollow area. And what that did is optimize the sensor for an extremely fast response time in liquid hydrogen, so about 20 degrees Kelvin, where everything moves slow and readings are slow, materials act funny at liquid hydrogen, and that's why the sensor needed to be designed in this format. And then over here, this guy over here, he's not a space sensor. He's sort of a standard piece of relatively industrial hardware that we supply to nuclear power plants. And so you have a probe, which is quite heavy duty in nature. It's real thick. It's much more similar to the one that's hanging out in the dry ice. And then on the back, it has a sort of shielded cable to protect it from extreme environment and radiation in a nuclear power plant. So some of the things that we have to think about when we're designing sensors for space are dynamics of launch. So that's high shock, high vibration, super noisy environment. Then once it gets into space, it might be in a vacuum. So you have to consider how the material is going to behave in a vacuum. Many of you probably familiar with off-gassing or out-gassing of materials in a vacuum, or anybody who's spray painted in a garage knows that there can be real bad side effects from fumes. You have the extreme temperature swings. We have things that are basically cryogenic, in the negative hundreds of degrees. And they may be experiencing then shortly after the actual combustion or ignition, right? And then we've also designed sensors that have landed on the surface of the moon. Famously, the moon dust or regolith, super problematic. A lot of different things you have to consider there. And also the system engineers who are integrating our sensors have to consider with that. Materials also, I should add, behave so differently at the cryogenic temperatures, especially when we're getting down into the liquid hydrogen temperature, LH2 temperature. You have materials shrinking and cracking and behaving differently, basically, than they would at almost any other temperature. And it's quite a specialized thing to work at that temperature. So it really is a specialty of RDF to design sensors capable of withstanding that. So I'll get into a little bit of our actual history now. So we know that RDF in the 50s, even before it ever arrived in Hudson, was involved in supplying the missile program. At this point, of course, the post-World War II, and now we're already into the Cold War, basically. There was a big rush to have missiles, that ballistic missiles that could travel a strong distance. And so RDF was already designing and building probes, monitoring and controlling, used to monitor and control the temperature in the guidance systems on the Minuteman and Polaris style missiles. And with the Juno missiles, we also supplied thermocouple reference junctions for those missiles. And then the Juno, of course, evolved into the Juno 2, which is one of the original rockets. And so because basically the Juno 2 was built as the missile, the Juno missile with a capsule on the top. And so those were actually used to launch the earliest Pioneer satellites into space. You probably can't make it out, but I found this notebook with the help of Kevin and Nate the other day in RDF's engineering department. And this page just lists tons of designs that they already had underway in the early 50s. And those designs included ones that would be appropriate for this, including the stick-on style, surface style RTD, and I don't know, others. I can't quite read it, but let's see. So that was followed up pretty quickly with NASA's Project Mercury. Project Mercury started in '58, but all of the launches took place basically late 1960 into 1961 and thereafter. So Project Mercury is, of course, the project that yielded the Mercury Redstone launch vehicle, which there is a gigantic model of right outside. And that is, of course, the vehicle that was used for Alan Shepard's first entry into space aboard the Freedom 7. And so we do, in fact, know that RDF had a variety of sensors on the Freedom 7. They were the surface types, which you saw earlier, used to monitor the temperature of critical electronic equipment throughout the first stage and also into the capsule. We also had probe-style sensors. In this particular case, we know that they were used to monitor the inlet air temperature to the pilot's pressure suit. I don't know if many of you are familiar with this story, but Alan Shepard famously became very upset the day of his launch because he needed to go to the bathroom really, really, really bad. And there were a bunch of delays that day. And so he had been on the pad for hours, unable to go potty, basically. And he had demanded that they let him leave to go to the bathroom. They would not let him leave. So he instead went in his suit. But that inlet air was working super good. And they knew the temperature of it. And he dried him out in a jiffy, and then he shot off into space. So excellent contribution to space exploration there by RDF. And we also, at that point, already had sensors installed in the heat shield, which at that time was made of beryllium. So yeah, whatever, this definitely isn't the exact sensor. That was the surface style, but it's probably pretty close. This one having been drawn in, I think, 1961, but the sensors we would have delivered to Freedom 7 would have been delivered maybe a couple years in advance of that. And within a year, we reached orbit, John Glenn famously piloting the Friendship 7, and we received a letter from McDonnell Aircraft Corporation, who manufactured that rocket, which actually wasn't a Redstone, it was a Mercury Atlas. And they confirmed that all of the RDF sensors, of which there were several models, functioned well during the flight. And then we're basically already well into the Apollo era, which of course was kicked off by President Kennedy basically within days of Alan Shepard's flight. He didn't even wait for the second guy, Gus Grissom, to make it into space. He already announced it like within basically 3 weeks of Alan Shepard reaching suborbit. And of course, President Kennedy famously launching a goal of landing a man on the moon and returning him safely to Earth, again, without us ever having reached orbit at that point. But we could see that in our review of the archives that we have, that RDF was already well underway in development of what the sensors would need to be in order to make this happen. We had to expand basically our measurable temperature range because the earlier rockets, they used liquid oxygen to help with combustion of the propellant, but that propellant was very similar to a kerosene type of chemical. It wasn't at all like the liquid hydrogen that was going to need to be used to do what's called heavy lift. So all of the vehicles in the Apollo era, they needed to be heavy lift vehicles, meaning that they needed to be able to not only get into orbit, but well out of orbit, right? Especially if we were going to make it to the moon. And so liquid oxygen actually is warmer than liquid nitrogen. So any of you that have had ice cream, liquid nitrogen ice cream, or your liquid nitrogen cold brew or whatever at Starbucks, just know that liquid oxygen is not even that cold. It's a little bit warmer than that. So liquid oxygen, basically, in order to measure liquid oxygen, we didn't need to expand the state of the art that much. Pretty much all of RDF's style of RTD probe can function in liquid nitrogen just fine. Just like that probe right there. Today we're using dry ice. If that was liquid nitrogen, no problem. But in order to change over to liquid hydrogen fuel, that was going to require some pretty serious development. And also other factors too. You can imagine with a launch like that, that there was going to be significant more of those dynamics, those launch dynamics to factor in. Not to mention everything needed to keep a crew alive up in orbit and get them to the moon, right? So actually over here we have one of the earliest drawings of a cryogenic probe that I was able to find last night at 8 p.m. in the closet. But in this drawing, we are already advocating calibration, actually, in liquid hydrogen. I have no idea how they achieved that, because liquid hydrogen is super unsafe to have around, but apparently we were capable in the Apollo era of doing calibration in liquid hydrogen. Today, we actually use liquid helium to do this function. Liquid helium is colder than liquid hydrogen, but it's a lot safer to have around. But I guess in 1961, our engineering was advocating the use of liquid hydrogen for calibration instead. And then over here, we have an example of a surface style RTD again, but this one was developed to withstand at least 1,500 degrees Fahrenheit, which is very, very, very hot. And it's a design which featured mica insulation, mica being that sort of shiny mineral you find at the beach, all the shiny stuff, sort of flaky stuff in rocks. So we were using that at that time to insulate the sensor so that it could withstand those high temperatures. And then moving on towards the moon landing, we have pictured actually the telegram that RDF received congratulating everybody on the soft landing of a surveyor spacecraft. We also know that RDF sensors were on the LEM module, which landed on the surface of the moon. And here we have Frank Hines, who you met earlier, and another former RDF president, Hugh Range, and two other of our employees at Kennedy Space Center with the module. And so all of this happened very quickly. I'm sure many of you recall that the space program really innovated on a very rapid time scale in the 60s. We achieved things in a time frame that today we basically never can. And RDF had to meet that rapid demand, not just to develop new technology, but to deliver it. And we were a success and were nominated in 1968 for the Small Business Administration Small Business of the Year for the work that we did supporting the space program. And after the Apollo era, we of course have, the Skylab era, America's first and technically only space station, because the International Space Station is international. So RDF did work to support Skylab as well, which was built using some of the leftover components of the Apollo missions anyway. But then pretty soon after, we are in the space shuttle era. So we, at this point, we're 20 years in to the space program. Things are, it's a little bit different than the early 60s. There's tons of systems in place now, and we're supplying temperature sensors to monitor all kinds of things. Coolant lines, engine exhaust, wheel well, these are just some of the things that I'm personally aware of. We also provided sensors that were embedded in plugs installed in the heat shield being something really special about the space shuttle, being, that the shuttles needed to be reused and so on. And the heat shield at that point was designed to ablate, meaning layers of it would sort of burn off as it entered the atmosphere. And so that was quite a specialty design for the sensors that we used for that. We participated in the spacesuit design. Spacesuit, honestly, basically like a spacecraft for one, right? Very challenging to make and design with full life support inside of a suit, right? We also supply sensors into the crew cabin, environmental and life support systems. My favorite one of these is, of course, the toilet system. Very famously, the toilets aboard Apollo and then later on the space shuttle. There's a lot of challenges around that design, not just because you have to find a way to collect waste in zero gravity, but also many of the systems attached to that were very innovative. We know for a fact that RDF sensors are still designed into the water reclamation system used on those the waste system, the toilet system. And actually that there's a very critical function where, especially those of you who've seen Apollo 13 will remember, you have to be very careful about ejecting ice into space at that location. And so the temperature sensors used to monitor the temperature of the waste being ejected is a very critical function. In 1976, we received some lovely materials from our customer showing the Space Shuttle Enterprise under construction and the location of RDF sensors in some of the new systems on the Enterprise. The Enterprise actually was sort of an experimental orbiter. It didn't have an engine system. It didn't have the same kind of heat shield. It was mostly designed for atmospheric test flights to see how it would perform. But it also included some new water and freon cooling systems throughout. And you can see some of the sensors locations are circled here in this avionics cooling unit. Somebody very kindly sent us a photo of with all these different locations there. We also know that they were installed in this system, which was not identified to me what it is, but I'm certain that monitoring the temperature was critical to it. And also this one, fabulous. But yeah, to be honest, I'm not sure what they do, but I believe that the coolant monitoring was very critical. Again, any and all questions directed to Art Pearson. And this is a view from our lobby at RDF. When we say we supported every manned spaceflight, we really mean it. These are just some of the flight patches that we have on display for the space shuttle missions. So to talk a little bit about the extravehicular mobility units, or EMUs. So again, this is an extraordinary achievement by so many companies, and of course by Hamilton Standard, who made it first. But you have to, again, remember, so many years of experience building spacecraft, now you have to put it into a literal suit, right? It's an extraordinary achievement, just to keep it sealed even, right? But now you have a human being inside of there, you've got to know if they're okay. So the temperature sensors of them, critical, right? But then you have this gigantic pack on the back, enabling them to move around. And the RDF sensors were throughout that as well. And so I think a lot of people at that time in the 80s, when this first rolled out, were probably pretty excited to see what's now very common to us, but this really was an extraordinary achievement. Some of the capabilities of these sensors was really highlighted in the Hubble Space Telescope rescue missions. I don't know if any of you are familiar with this, but it's the first time I ever learned about this was this week. So we all know what the Hubble Space Telescope is. Some of us may not recall that when the Hubble Space Telescope first launched, it was a publicly considered failure because the images that started coming back were out of focus, some of them. And so it became realized that the mirror that accompanied the telescope, in which it was meant to enable it to get these pictures, the mirror wasn't quite right. And I believe that it was basically off by nanometers, but that just goes to show you how precise things need to be in space for it to work out. But NASA had put huge resources behind putting the Hubble Space Telescope in space. And, public opinion has always been challenged when it comes to space. Many people feel that money and funding directed towards space exploration would be better directed elsewhere. And so it became a serious public image problem for NASA that the Hubble Space Telescope was not working as intended. And they were concerned about public support draining from the program, from the shuttle program. And so they embarked on a very ambitious program to fix the telescope in situ, to fix it in space. And so there was a rush to ready the shuttles, ready the crews, provide them the training necessary to perform a much more hands-on repair than had ever been expected in space. And that, of course, also required rapid development again and build again of spacesuits. And the spacesuits manufacturer, Hamilton Standard, again, they won what's called the Collier Award for the work on that. It's the highest ranking award you can get in aerospace. And they in turn awarded RDF for the work that our machine shop and our special products division did on a tight time scale to support what was needed for those spacesuits in order for the astronauts to perform a much more challenging spacewalk than had ever been intended. And actually the NASA completed 4 rescue missions to the Hubble telescope, the Hubble Space Telescope, the beginning, I believe, in 1994 and ending several years later. I happened to be at breakfast with this guy the other day. Scott Altman, or Scooter Altman, commanded 3 of those 4 rescue missions. We had a long conversation actually about what we did to contribute to that, and he told me that his crew members were really struggling with concern and fear about making the spacewalks needed to perform these repairs. You can imagine, the dropping of a screw or the dropping of a tool in space being a much bigger deal. And these gloves are very bulky and actually required heaters, like newly developed and improved heaters to be built into the gloves in order to keep them warm enough to do these small kinds of tasks. He, of course, didn't make the spacewalks because he had to fly the thing. So they didn't let him out into space, but he told me that his colleagues were very grateful to have the improved spacesuit and improved spacesuit design, that it made a genuine difference to their lives, and that really warmed my heart. So it was a great conversation that I had with him, and he sent over this to share with our team about the impact that had with them, because several of the people pictured in the previous slide, they're still with us at RDF. We still work with them every day. Say thanks to Lisa Essig, those of you who were from RDF. It was really an extraordinary achievement. Also, a fun fact about Scott Altman, he is the guy who performed all the stunts in Top Gun, which I think is pretty impressive. I told this story the other day to Nate and Kevin said, "What, the original Top Gun?" Which made me mad. Also in the 90s, RDF was awarded the Silver Snoopy, which is an award given by NASA to companies or individuals who make a very significant contribution to the safety related to human spaceflight. And in this particular case, an RDF engineer named Bix Hamby alerted NASA to scrub a mission. It's actually Columbia flight 40 there, after discovering a flawed or leaking liquid hydrogen sensor the day before launch. And so of course, we like to deliver quality hardware. We never want to hear that something actually wasn't working, but it is commendable that this gentleman stood up and informed NASA that there was a problem, and for that we were given the Silver Snoopy Award, which we are very proud of. And a few years later, sadly, of course, the Columbia disintegrated on reentry over Texas, I believe, Texas and Louisiana, I believe, which is an incredible tragedy, and all 7 astronauts did die. The RDF sensors actually were installed in the 80s and were still functioning at the time of the disintegration. And so you can actually see sensors here in this left wing area, it's circled in red, and up here in what's called the bipod area. They were very critical to the investigation of what caused the disaster. So again, they were installed in the 80s, and they had been working, serving their data collection purpose for more than 20 years, and then they actually continued and survived the disaster. So readings from those sensors, which were recovered, actually enabled some of the analysis necessary for the accident, and then that information was pretty critical in what later became known as the return to flight program, because some of you, again, may recall that all of the shuttles were grounded following this disaster. There was a lot of controversy over whether they would be enabled to fly again, whether there had been enough safety measures taken. Yes. Oh, sorry, it looked like you were doing this. Okay. So yeah, it really speaks, I think, to the exceptional care that is taken at RDF in our design and in our manufacture of products. Sometimes, we really go the extra mile where that is the case. We never build for obsolescence at RDF, planned obsolescence. The things we build have a tendency to work way beyond what we expect them to, and this really is a testament to that. And finally to today, of course, the shuttle program ended in 2011. And shortly after that, there was another program called Constellation, which was canceled during the Obama administration, which was a huge jolt to the space program and all of the companies, RDF included, who contribute to that. But after that, NASA introduced the Artemis program. Just quick show of hands, how many of you are familiar with the Artemis program? Oh, okay, like everybody, right? So that sounds good. Well, Artemis basically is, of course, the twin sister to Apollo. She's the goddess of the hunt and many other fine things, I believe. Also goddess of the moon, and where Apollo is god of the sun. And so NASA's Artemis mission is to return us to the moon, but not just return us to the moon, but then take us to Mars. And so this is a very exciting program, and it began with the design and build of what's known as a Space Launch System. So you probably can't tell looking at this rocket here, or this image here, but it's extremely tall. It's much taller than the Statue of Liberty. It is by far the biggest rocket ever built and ever launched. We delivered hundreds of sensors to the core stage here. This bit that's basically in orange. We had, I believe, more than 140 new designs in total that flew on Artemis 1 in November of 2022. Above that is the Orion capsule. It's this bit here. So that is, of course, intended to become the crew capsule, but when Artemis flew in November 2022, it was not crewed. It was an uncrewed mission, but still a test for numerous new designs that we have embedded through there. And some of those systems will, of course, become the environmental and life support systems down the line. Artemis 2 is expected to launch in a couple of years, and that will be a crewed mission. And so we've already built and delivered those sensors years ago for that. I'm actually wearing a little bit of Orion tonight. In this pin, I have shavings from the first Orion craft. I'm told by the person who gave it to me that this pin also traveled around the moon. Orion did make the longest journey of any spacecraft that we've shot to the moon. It didn't land on the moon, but it made quite a journey around it and back, which was successful. So RDF is fully invested in our participation to the Artemis program. I'll put this up. Of course, it's an artist rendering because we haven't made it there yet, even though Odie, Odysseus from Intuitive Machines, landed last week, I think. So we've already built many of the sensors that are expected to take Artemis 3 and the third Orion spacecraft to the moon, which would be the first anticipated landing of a woman and person of color on the moon, and very hotly anticipating that. But we're also already in the proposal and design phase for all of the other architectural pieces to this system. That includes the human lander system. So we were on the first lunar module. We plan to be on the next. That work has been awarded to our customer SpaceX and our other customer Blue Origin. So we're very excited about the work we're doing on that. And also the Gateway, which is planned to be the cislunar space station, enabling permanent presence at the moon with missions up and down from the Gateway to the surface, and then launched from the Gateway to Mars, which is very exciting for those of us in the generation at RDF who did not live through the previous exciting programs. This is everything we're invested in for the future, and my favorite. So with that, I don't know if any of you have any questions. I'd be happy to direct them again to Art, but.
So do all these sensors, for example, do some of the sensors record something and then you can peel it off and plug it into a machine to read what the ultimate temperature was? Or do they have to have a constant, steady, regulated flow of electricity that you then can measure out through time in real time?
It's a second.
It is that.
It's a second. Yeah. So, and that's what's important and critical for their use. You want to be able to have constant measurement over a long period of time. So going back to the design of some of these sensors and some of what makes them special, we actually qualify them for survival in very challenging environments, either through a launch activity, which is super violent, or for a length of time, or sometimes both. Actually, some of our nuclear grade sensors have been qualified to survive in a nuclear reactor for more than 30 years. So it's very critical to their purpose that they be a continuous measurement. Yeah?
Do your products mainly built for purpose, or do you have any mass consumer?
So we don't really do anything that's mass consume in that we don't produce anything at a volume which is considered like mass volume, but we do have a number of commercial grade or catalog style sensors. Basically all of the ones that we showed you here, all of these are catalog sensors. You can buy them from stock, hopefully, usually most of the time. They're even sold in some catalogs by some catalog companies like Omega and so on. But all of our products are premium in the marketplace, meaning that you can probably find something similar that's cheaper, but they may not, actually definitely do not have the performance capabilities of even our standard or commercial grade products. And our standard and commercial grade products have flight pedigree too. All of those have flown. All of them can fly, and we still sell them to NASA or whoever whenever they need it.
So when would a normal person in the course of their normal life, not an astronaut or not a nuclear engineer, run into one of your sensors?
That's a great question, actually. Anytime you fly a commercial aircraft, so one of our earliest products, way back in at least the 50s, were for sensors that are embedded in the glass in front of a pilot flying commercial aircraft. I'm sure some of you have seen videos of birds flying into plane windows and of them absorbing the impact or breaking. So in order to mitigate that, that window needs to be heated to a very specific temperature. And we make sensors which are embedded into the many layers which make up that window to monitor the temperature, and they're hooked into the control units to keep that temperature stable. We build thousands of them. Sarah over there has fielded, I don't know how many orders this year alone for those kinds of sensors.
Well, not always all the questions.
Oh, please, go
If
right
anyone
ahead.
else has them.
Oh yeah, go ahead.
So, the primary temperature sensing piece, how many different ones of those? In other words, is it functionally the same thing, just being tweaked and morphed into all these different exterior shapes and
Well, I'm so glad you asked, because it reminded me that we did bring all of this. So again, like the sensor itself is not always what's changing, it's really the packaging, right? And so a great way to see this is actually in these chip style sensors up here. So in the beginning, I showed you a cylindrical style wire wound RTD, and then I showed you a surface style wire wound RTD. But then, basically in the 90s, we started putting them on chips. And so you can imagine, like inside this, inside that, inside this, even inside this, there's a chip. So the sensor isn't changing, but everything around it changes to suit the application that it's going into. So actually over here too, if anybody's interested, please come have a look. We've got a display over here, but you can see any number of designs. They all look different. Some of them even just look like a bolt, but they all have almost the same thing on the inside, but everything around it changes.
so what about, is there any research going on about changing that innermost sensor model, different metals or different configurations or micro-sizing it more?
Sure, all the time.
Is that you guys that do that, or do you just take advantage of it and then you can apply it to what the need is?
Well, one of the great examples there, I think, is work that we are looking into with Idaho National Labs. This is nuclear-related work, but existing thermocouples don't have the capability to monitor temperature accurately above a certain point in a heavily radiated environment. And so that's an area in which we're looking at changing the metals used. But there are challenges with that, because it's not just something that a couple of PhDs can make in a lab that becomes a sensor we can use out in the real world. It has to be something that we can all make, and make reliably and over again, and have the same every time we make it. So innovation in this space takes a long time. But we are always keeping an eye out on other things that we can do in the meantime. Sometimes it has more to do with the packaging again than it does the actual sensing element on the inside. And another thing with that too is that although this is very mature technology, it's very good technology. A lot of the experimental tech that's out there in this kind of temperature measurement isn't quite there yet. But there are, of course, other types of sensors that you can buy, even ones that are contact temperature sensors, like a thermistor. For example, I don't know if you've run into that, but a thermistor basically works just like an RTD, but it has a much narrower temperature range. So the Platinum RTD is still the superior product, very mature, but very superior depending on the application. Go ahead.
With any package unit that have like a conditioned high output, say like a 420 milliamp, or are you just working on the very base output of the actual sensor itself?
I'm not sure I understood your question, but I think your question has to do with signal conditioning, maybe? Like
Yeah, some packages of want
Yeah.
to have, electronics right there in the package and they're putting out a high-level signal, which is a lot more noise than you.
There certainly are products available on the market that are optimized for that or include everything as an all-in-one kit. We don't currently sell them in kits like that because oftentimes our customer is an engineer who is a systems engineer somewhere who has a very complicated integration that they're looking to perform. And they don't really want that kind of a thing from us. But absolutely
They
there are,
just want the raw signal.
they do, they want to input it the way they want to into the crazy thing they're making. But absolutely, there are products available, with other temperature sensors all in a kit that you can get. Any other questions? You had one. He asked
He
it.
stole my question.
Well, with that, I guess, thank you guys for spending your Friday night with us. And I hope that, you learned something you found interesting. We'll be around for a bit if anybody has questions. And I'll stand next to Art.